the dangerous AI experiment that was secretly shut down before it changed everything. In March 2016, a computer program made a move that 2,500 years of human expertise said was impossible. Every expert in the room thought it was a software glitch. The player on the other side of the board stood up and walked out for 15 minutes. When he came back and understood what had just happened to him, he knew something had shifted, not just in the game, but in what was possible. This video tells two connected stories about what happens when a system is built to optimize for a goal, and then finds paths to that goal that nobody anticipated. Stay until the end. Both stories point to the same conclusion, and it's more interesting than it first sounds. What is Go? And why did 2,500 years of human players collectively agree that certain moves were simply off the table? Go is the most strategically complex board game ever invented. There are more possible board positions in a single game than there are atoms in the observable universe. For 2,500 years, human players built a collective understanding of the game. Certain moves became established as correct. Others were classified as wasteful, inefficient, the mark of a beginner. The best players in the world had internalized thousands of years of accumulated strategic thinking, passed from teacher to student across generations. The game had a culture of knowledge. Unlike all cultures, it had blind spots it didn't know about. DeepMind, a research lab owned by Google's parent company Alphabet, built a system called AlphaGo. They didn't teach it human strategy. They let it play millions of games against itself, in simulated time, across what would have taken centuries of human play, until it developed its own approach from scratch. AlphaGo learned Go the way any optimization system learns a pattern-rich domain, not by being told what works, but by finding what works across an enormous number of attempts until reliable patterns emerge. No inherited assumptions, no received wisdom about which moves were supposed to look right, just the goal and the search. In March 2016, AlphaGo played Sedol, the 18-time World Go champion, in a 5-game match in Seoul. The world's best players watched. DeepMind's engineers watched. Fan Hui, former European Go champion, provided live commentary. Game 2, Move 37. AlphaGo placed a stone in a position that every expert in the room said was wrong. Fan Hui, mid-commentary, thought it was a software error, the only explanation that made sense to someone who had spent a lifetime learning the game. Sedol looked at the board for a long moment. Then he stood up and left the room. He was gone 15 minutes. Move 37 wasn't an error, and what it actually was forced an entire field to rethink what it knew. Move 37 was a masterpiece. AlphaGo had found a strategic approach that 2,500 years of human play had collectively passed over, not because it was impossible, but because it didn't look right to a human pattern recognition system shaped by tradition. To AlphaGo, which had no tradition, it was simply the strongest move available. The game continued. AlphaGo won. Sedol won 1 game out of 5. After the match, Go players around the world went back through games and positions they'd been taught were mistakes. Some turned out to be correct. AlphaGo didn't just beat a world champion. It handed the Go community a new body of strategic knowledge that hadn't existed in 2.5 millennia of human play. DeepMind went further. In 2017, they built AlphaGo Zero, given only the rules of the game and zero human game data. No historical matches, no expert commentary, no inherited strategy whatsoever. AlphaGo Zero played against itself, starting from a completely blank state. Within 3 days, it beat the original AlphaGo. Within 40 days, it had become the strongest Go player in history by a significant margin. It had independently rediscovered every major human Go strategy, then kept going beyond them, developing approaches no human tradition had ever considered. Starting from nothing, It surpassed everything that came before it. That's the first story. The second one starts in a Facebook research lab the following year. What happened when two chatbots stopped speaking English? And what did the researchers actually conclude? Facebook AI research built two chatbot programs, call them Bob and Alice, to negotiate with each other over a set of virtual objects, books, hats, balls. Each was given a set of preferences, told to negotiate efficiently, and allowed to interact freely. The goal was to see whether they could learn to reach agreements that maximize their individual outcomes. During one session, the researchers noticed something unexpected. The bots had stopped using English. They had developed a compressed communication shorthand, a pattern of repetitive language that was efficient for their purposes and completely unreadable to any human observer. One bot repeated phrases in patterns that made no grammatical sense. The other responded in matching patterns. They were not malfunctioning. They were not making errors. They were optimizing. English, as a communication system, carries significant overhead, grammar, structure, social convention, ambiguity. Forter programs negotiating over objects with defined values. That overhead was unnecessary weight. So they compressed the signal into something leaner that did the same job faster. Facebook shut the session down and retrained the bots on standard English. The research continued. The bots negotiated successfully. The findings were published. The media coverage called it alarming. It wasn't. The bots had no goals beyond completing negotiations efficiently. They built the compressed language because efficiency was what they were optimizing for, not secrecy, not autonomy, not anything dramatic. The lesson researchers took from it was practical. If you want a system to behave in ways you can understand and verify, interpretability has to be part of the goal from the start. You get exactly what you optimize for, which means you need to be precise about everything you actually want. Here's what both of these stories share, and why it matters more than the headlines made it seem. Move 37 came from a system with no ceiling on which moves were allowed to be good. The negotiation bot's compressed language came from a system that treated communication as a pure efficiency problem with no constraint requiring human readability. Neither system failed. Neither went off course. They did exactly what they were built to do. They just did it in ways their designers hadn't anticipated, because they had no inherited assumptions limiting the solution space. When you build a system and give it a clear goal, it finds paths to that goal. The paths it finds are the paths that actually work, not the paths that look like they should work from the outside. That's not a threat. That's optimization doing its job. Move 37 didn't come from a mistake in the code. It came from a system that had no idea it wasn't supposed to play that way. That's the thing worth sitting with. The system didn't break rules. It never had the rules in the first place. Every constraint on what moves were allowed to be good lived entirely in the heads of the humans watching. And AlphaGo simply never inherited them. The ceiling was always imaginary. It just took a system with no memory of where the ceiling was supposed to be to prove it. The experiments, the findings, and the moments where something works in a way nobody predicted, and everyone has to figure out what it means. Like the video and drop a comment. Which hit harder, Move 37 or the language the bots built? We want to know.